Hello everyone, this is Teka and you are watching me on my YouTube channel Chemistry Tutorial. So guys, in this video we are going to discuss about the solution of the azimuthal part and the polar part of Schrodinger equation. In the previous class we have discussed about the radial part of this Schrodinger equation, and we have seen different radial wave function for different values of angular quantum number and the principal quantum number. Here we will see what is the polar equation and what is the polar wave function and the azimuthal wave function. Okay, so let's see what is the polar equation first. The polar equation was d square theta divided by dp, sorry, it should be p, since p is the function, okay, theta is the variable. So cos theta divided by sin theta dp d theta plus beta into p equal to m square divided by sin square theta into p. This is the polar equation we have found in the first class of hydrogen atom, okay, in the discussion of hydrogen atom. Here you should remember what is the value of beta. Beta is generally expressed as L plus 1, okay. This L, it is the angular quantum number. So since it is a second order differential equation, this the solution of this differential equation is very lengthy. We are not going to the method of solution, we just go to the what is the value of this solution, and the solution will be a polynomial, that is p, okay. This polynomial will be a function of theta. This polynomial will be a function of theta. It depends upon two values, that is one is called L and other one is M. Here L, it is the angular quantum number. Here L, it is the angular quantum number, where M, it is the azimuthal quantum number. So this polynomial is called associated Legendre polynomial. Associated Legendre polynomial. So when m equal to, this is the solution, okay. I'll now show you what is the expression of this polynomial. So since it is a function of theta, now we'll express as a function of x for sake of simplicity. To express as a function of x, we need to consider x as a x equal to cos theta, okay. We consider x equal to cos theta. So this polynomial, it is given by a normalization constant. Since it is a wave function, there should be a normalization constant. So it is given by 1 minus x square m by 2 mod of m by 2 ddx m by mod of m by 2 and 1 by 2 to the power L factorial L ddx up to Lth term, okay. Here we have considered m by 2 term, ddx up to L term. There should be a bracket, ddx of x square minus 1 to the power L. So this is the expression for this polynomial, okay. This is called associated Legendre polynomial. Here in this case you see this part, from this part to this part, it is called Legendre polynomial. This part, it is called Legendre polynomial. The whole part, it is called associated polynomial, and this part of this expression, it is called Legendre polynomial. It is generally expressed as it should be p L x here, okay. This is called Legendre polynomial. So this is the solution of this polar equation when m equal to, you must consider this, when m is not equal to 0. Okay, the solution of polar equation when m is not equal to 0 is expressed as a associated Legendre polynomial. But when m equal to 0, the solution of this polar equation, it is given by Legendre polynomial. So what is Legendre polynomial? We have already write here. So this is the expression for Legendre polynomial. I am writing here over. Okay, again it is given by normalization constant 1 by 2 to the power L factorial L ddx up to L term. Okay, derivation up to L term with respect to x, and x square minus 1 to the power L. So this is the solution of polar equation when m value it is 0. Now we'll see the value of normalization constant. What is the value of normalization constant? So, and it is the normalization constant, its value will be twice L plus 1 divided by 2 into factorial L minus mod of m divided by factorial L plus mod of m whole to the power 1 by 2. Okay, here you see the values of L it is the angular quantum number. Its value will be 0, 1, 2, 3 up to there. Okay, n minus 1. This is the principal quantum number, and the value of m would be from 0. Okay, I am writing here plus minus L minus 1 plus minus L minus 2 up to 0. So these are the values of m, that is azimuthal quantum number. Okay, so these are the expression for normalization constant and polar wave function. These are the expression for normalization constant and the polar wave function for polar equation. Now we'll see different polar wave function for different values of L and m. Okay, now we'll consider different combination for L and m and what will be the polar wave function. So alright, first we consider L equal to, first we will consider m equal to 0. For m equal to 0, the values of L might be 0, 1, 2 like that. Okay, so first we will consider the combination of L equal to 0 and m equal to 0. So when m equal to 0 and L equal to 0, since here m is equal to 0, the solution of the polar equation will be given by the Legendre polynomial. Okay, so it will be expressed as Legendre polynomial. So what will be the Legendre polynomial? 1 by 2 to the power L factorial L ddx, okay, up to L term, and x square minus 1 to the power L. So this is the expression for Legendre polynomial. So here we will put 2 to the power 0 L factorial 0 ddx up to 0 term and x square minus 1 to the power 0. Okay, 2 to the power 0, anything to the power 0 it is 1. Factorial of 0 it is 1. It also be 1 and this is also 1. So your result is 1. Okay, so this is the solution of polar part when m equal to 0 and L equal to 0. Okay, I'm not here calculating the normalization constant. I'm just calculating the polar equations. So now let us consider when m equal to 0 and L equal to 1, what will be the polar wave function. Here also it is expressed by the Legendre polynomial 1 by 2 to the power L factorial L ddx to the power L term x square minus 1 to the power L. So here L value it is 1. So you put here 1, 2 to the power 1 factorial of 1 ddx into x square minus 1. Okay. So 1 by 2 into this will twice x. Twice x, twice x. You cancel out. You will have only x. We know x equal to cos theta. So PL theta will be cos theta for m equal to 0 and L equal to 1. There will be a normalization constant also, but I am not calculating the normalization constant. Now let us calculate the Legendre polynomial for m equal to 0 and L equal to 2. So when L equal to 2, what will be the Legendre polynomial? Here 1 by 2 to the power 2 root over 2 ddx 2 to the power 2 x square minus s square 2 to the power. So this is 8 ddx into ddx. Okay, so it would be x to the power 4 plus 1 minus of twice of x square. So if we derive this term with respect to x, then we will have ddx 4x cube and 4x. Again, if we derive this term with respect to ddx, then we will get 4 can be common out. We can take common out of it. So it will be 1 by 2, 4 will cancel out, 4 and 8 will cancel out and give you 2, and we will have 3x square minus 1. So in place of x you can write, so this is the Legendre polynomial which is the function of x. So if we put x equal to cos theta, it will be a function of theta. So in place of x square you can write 3 cos square theta minus 1. Okay, so this is the Legendre polynomial when m equal to 0 and L equal to 2. Now we'll see when m is not equal to 0. So when m equal to 1, the value of L might be 1, 2 like that. Okay, we'll consider just two values of L. So let us consider when m equal to 1 and L equal to 1. In this case, the solution of polar equation, that is polar wave function, it will be expressed as a PLM, that is associated Legendre polynomial. So it will be 1 minus x square to the power m by 2 ddx m by 2 1 by 2 to the power L root of factorial L and ddx to the power L x square minus 1 to the power L. Okay, this is the expression for associated Legendre polynomial. Now we'll put the m and L value and we'll derive the expressions. Okay, so when here L equal to 1, and m equal to, so x square by 1 by 2 ddx. I might have done a mistake here. This ddx should be up to m term, okay? In the main expression I might have write in the this m by 2, okay? You just correct it. This should be up to m by, okay, up to m term. So m here it is 1. So 1 by 2 to the power 1 factorial of 1 ddx x square minus 1. This much we know, this much is equal to x we have already calculated. So dd of x it will be 1. So your expression will be root over 1 by x square. So 1 by x square would be 1 minus cos square theta. This is equal to sin theta. So your associated polynomial where L equal to 1 and m equal to 1 is cosine theta. Now we'll consider m equal to 1 and L equal to 2. So when m equal to 1 and L equal to 2, what will be the expression for, what will be the value for associated Legendre polynomial? So in this case you say 1 minus x square to the power m by 2 would be half, okay? ddx it will be 1 and 1 by 2 to the power 2 root over 2 dd of x square minus 1 to the power square. Okay, we know this value will be come out as 4 into, okay, this will be as a result half of 3 x square minus 1. So if you derive this term with respect to x, then it will give you 1 minus x square, okay, root over half will come out and 6x 3x, okay. So 3 into cos theta, this will give you sin theta. So the associated Legendre polynomial when m equal to 1 and L equal to 2, it is 3 cos theta into sin theta. So this is how you can calculate the different polar wave function for different values of m and L. Here I am not calculating the normalization constant, okay? So you do it at your own. The normalization constant, it is very easy to calculate. I have already given the formula to calculate the normalization constant. It is generally given by n equal to twice L plus 1 divided by 2 L minus 1 factorial L minus 1 divided by L plus m, okay, L plus m whole to the power half. So you can do it at your own. This is very simple. Now we'll see the solution of the azimuthal part of polarity, now we'll see the solution of azimuthal part of Schrödinger equation in case of hydrogen atom. So the azimuthal equation was minus 1 by f d square f d phi square equal to m square into f. There should not be any f, okay. The solution, it is expressed as f as a function of phi. It is given by a normalization constant that is 1 by root over twice pi e to the power plus minus I m phi. Okay, so here m, it is the azimuthal quantum number, and its value will be ranges from plus minus L minus 1 plus minus L minus 2 up to 0. So these are the values of m, this m. Okay, so these are the solutions of different part of Schrodinger equation in hydrogen atoms. So these are the different solutions of the different part of Schrodinger equation for hydrogen atom. We can calculate this wave function separately, and at the end of the solution we can just combine all the solutions for a specific value of n, specific value of n, l, m. Okay, and ms would be also there. These are quantum numbers. Okay, so in the next video we will discuss the whole wave function, that is spherical harmonics. It is generally represented as spherical harmonics, the complete wave function for hydrogen atom or hydrogen like atoms. We will discuss that in the next video. For today's, this is it. We will not discuss anymore. So guys, I hope you have understand all the things I have discussed here. If you have any doubt, you can ask me on the comment section below, and if you are new to this channel, then subscribe our channel and don't forget to press the bell icon so that you can get the notification of uploaded video. You can follow us on our Facebook page and Facebook group, and the link of Facebook group and the page are given in the description box. Okay, so this is it. See you in the next video guys. Till then, thank you.